Hello there. Good afternoon, everyone. So it has been quite some while. Um, Today we are in week 18. Uh, Today I have some really important announcements to make. As some of you may know, this year's math count competition is in full swing. Many chapters across the nation had their chapter competitions yesterday. Although Mathcounts has almost a 1 month window, I believe 4 weeks, to allow chapters across the nation to choose a particular day, most likely weekends, to just conduct their competition. So a few local chapters did that yesterday here in Silicon Valley, Bay Area. I also know, I happen to know some chapters, say on the East Coast, also did it yesterday. Uh, the reason I mention that is because I have actually two interesting stories to tell today before we go to our weekly materials. So the story are quite unusual. So let me first get you a picture here. Okay, so uh, this young gentleman, his name is Aaron. So the picture you see right here, I'm not sure the stream is working. Okay, so the picture here is about a young gentleman by the name of Aaron. Uh, the little trophy he holds in his hand is a chapter competition third prize, not the first prize, third prize. And that chapter is a local chapter in South Carolina. Aaron happens to be my elder son. He's already in 8th grade. And this is his very first time to compete in Mathcounts. And I have been teaching Mathcounts. This is the third season publicly. So that means that he never took part in Mathcounts competition when he was a 6th grader or 7th grader. And more interestingly, he's way, way away from me. I'm in California here. He is in South Carolina, coast to coast. He will be 14 later this month. He actually is in a boarding school, a military boarding school. Name is Canada Military Academy in South Carolina. So he has been there since 7th grade, meaning that more than a year ago when he started as a 7th grade, he went there. So the very reason we chose to send him there to attend a boarding school is because ever since the pandemic began in early 2020, Aaron stopped studying essentially because the school went online as every other school in the country. And every time he was in class, he was just playing video game with his pals and with all kinds of just tricks to hack my routers, just pretend he was in class and just effectively did not learn anything at all. He did not learn anything, literally. So before that, that was I think it was the second half, the spring semester of his first 5th grade. Before that, Aaron did not do much math competition until in the second half of his 4th grade. Unlike many Chinese parents, I did not like to push my kids to study competition math really at a very young age. I genuinely think that's unhealthy and counterproductive. So we never sent him to any extracurricular math classes. We did send him to various sports, just classes, you name it, whatever you can think of, mostly. So he tried a lot of things. Also, he only settled with basketball, but we never sent him to any math class. So Aaron did not study competition math until in the spring semester of his fourth grade. So I've spent quite some time with him. We spent about half a year to study AOPS pre-algebra. So he did finish that book in about 6 months. Actually, a little bit less than 6 months. So in the summer before the fifth grade, I thought that he should prepare for AMCA as a rising fifth grader, but he did not do much. Actually, did not do anything at all to prepare for AMCA. I became really both angry and frustrated. Only when the fifth grade began, I forced him to do pass AMC exams. So he studied for about 2 months, I believe, maybe 2.5, or plus or minus. So he did take AMC 8 in that November when he was a fifth grade student. He did reasonably well. Not great, but he was okay. That year, because each year the cutoff scores fluctuated, so he missed 5%. At that time, it was called high honor or something. Missed that 5% high honor roll by 1 point. I believe he was 18. That year happened to be a relatively easier year. So I believe to get into the top 5%, you need to be 19. So he barely missed that. He was 18. Well, consider he only studied ALPS pre-algebra for less than a year. I thought that was pretty decent. However, soon later, when the new year came, the coronavirus pandemic began, and that he just entered into a prolonged period of long non-study mode. We tried everything, tried to force him to study, but he refused, and we could not do anything about it. So that continued for more than a year. And out of desperation, we sent him to a boarding school in South Carolina. There were various reasons we sent him to that particular school, but I don't need to just detail those reasons. But he ended up there. He continued not to learn competition math for about a year. In that year, I specifically opened a Russian geometry class. I want him to study for 1 year real geometry, meaning that the proof-based geometry. But unfortunately, he did not do much either. I tried everything, so he did not listen. He barely just followed the lectures, but did not do much about the homework. And in math study or pretty much any subject, if you don't do homework, then it will not be very productive. Not a good idea if you study math without doing homework. So I don't think he really learned much from that year, my geometry class. So then he turned 8th grade over the last summer. So I asked Aaron, so we talked about Mathcounts even before you were eligible, right? Because that was before the 6th grade. You cannot do Mathcounts until you are in 6th grade. So now you are in 8th grade. What do you want to do? So very reluctantly, he agreed to do math counts for this year. So we started working on math counts, and perhaps he became a little bit more mature. So he became quite serious. He trained for math counts for about maybe just one semester, right? Um, less than half a year. So yesterday he participated in South Carolina chapter competition, and usually a smaller state like South Carolina is much less competitive uh, as in California. But it happened that in that particular chapter, there were two, not just one, but two students who were on South Carolina's national team last year, meaning that they went to Mathcounts National as seventh graders last year. It's extremely difficult to go to Mathcounts National in any state, even a very small state. So that means that there were two really, really good students in his chapter. But he ended up well. So the two guys who went national last year got 43 and 41, and Aaron got 39. Not too bad, I think, for where he came from. So I think this is a story worthwhile for me to tell, because I think for competition math, it doesn't matter when you start. If you start really late as Aaron, he did not do any math count until in 8th grade. It's still totally possible for you to, make significant progress and became more interested like Aaron did. And then he really just tried hard this year because he knew this would be his last year. And he did okay. He qualified for South Carolina State. Although South Carolina is not that competitive, but I think it's still a very good experience, perhaps a very good start for him for the next couple of years. I think he will definitely do AMC 10 this fall. We will work together on that. But the takeaway is really, if you never did math, competition math before and you feel you're way behind other guys, that's a wrong assumption. You can start at any time. The only thing you need is some motivation, and more importantly, some joy when you start in competition math. I believe Aaron now is at a stage that he genuinely became more interested in competition math. And that's something you cannot buy with money. No matter how many extracurricular classes your parents send you to, if you are not interested, if you did not find really just enjoy the both things in doing math problems, even you can get very good scores in competitions, I don't think you will go very far. I don't know how far Aaron will go in the next couple of years, but I do want to help him to nurture such, newly found interest and go from here. So that's the first story I want to tell. Okay, it's never too late to study competition math. And you will be okay as soon as you become genuinely interested. Okay, that's my first story. I hope it's a good one. Now, let me tell you a very different and contrasting story. Okay, that is Aaron. Okay, this is my friend Andy Liu. Maybe some of you recognize him. And he also holds a trophy right? And this trophy, unlike Aaron's was third place prize in the chapter. What Andy holds here, if you can see, is first prize. I hope you can see it. It's really small, but this is first. And the background there, of course, the reason I can post this photo is that this is truly public. So a lot of people saw this live yesterday. Here, also in the local Mathcounts chapter here in the Silicon Valley, it's in Fremont, East Bay. The several local Mathcounts chapters here in Silicon Valley are extremely competitive. Actually, the Bay Area, the Silicon Valley in particular, is perhaps the most competitive place in terms of math competitions. The reason is simple. A lot of high-tech workers, engineers, scientists are here, so they tend to push their kids to study math. What is extraordinary is that Andy is just a sixth grader. He just got qualified for Mathcounts for the first year because that's the earliest you can do Mathcounts. And he competed in the extremely competitive chapter in Fremont. And didn't I say that the two national finalists from South Carolina got 43 and 41? And you know the individual full score is just 46. You got 30 from Spring, you got 16 from Target. Guess how many points Andy got? He got 44. I never heard of this. I mean, for the people or students that I know. Last year I had a student who happened to qualify for the national from California, meaning that he made the top 4 in California in the state. Of course, state competitions is much more challenging than in the chapter competition. But that same student also got just 41 in the chapter. It was quite interesting because he got exactly the same score in both chapter and the state. But that also tells that even chapter is less kind of just difficult than the state competition. It's still very difficult to get a high score. And he got 44 yesterday. That was extraordinarily good because Mathcounts, it's just you have to finish a lot of problems within a very short time frame. And he just missed 2 spring problems at the end, and he got all the target problems correct. That was super impressive. And most of all, he did not even have a team because his school, he happened to be in elementary school, and that school did not sponsor Mathcounts. So Andy had to participate as a non-school competitor, meaning that he is not affiliated with any school. He just compete as an individual. And he got the #1 place in the Fremont chapter. So it's very, very impressive. But how did Andy got here? I happen to know Andy for some time. Actually, unlike many kids, at least per his mom, before this year, not until recently, he did not actually take many extracurricular classes before. But Andy has been a very motivated, brilliant young kid. He took 2 years of math class from me, and the first year he just went through exactly this same 30-week Mathcounts training as a 4th grader. And then last year, he spent 1 year with me to study Russian geometry. According to his mom, he did not take any other outside classes until later this year. I mean, no, not this year, but 2002, from the Thinking Academy, the 学而思 from China. But other than that, he did not actually take outside classes. But I did kind of gave Andy very individualized coaching, or just providing suggestions from time to time on how to study math. I really encourage him not to pay too much attention to math competitions like AMC or Mathcounts. I think it's far more important to get a very fundamentally solid just education on basic stuff, and then read a lot of good books, math books, and maybe beyond math books. So I think a lot of students try to focus on get scores, good scores in competitions, and ignore willingly or just unconsciously ignore the importance of reading good books. I think that's a big mistake. So Andy actually started quite early, and he got extremely good result. And by the way, in last year's AMC 10, he was definitely within top 5% in both A and B, and just missed 1%. I think that's the HHR or something, distinguished HR, just by maybe a single problem in AMC. So it's not just match count. Andy is extraordinarily strong as a sixth grader. So this story also tells that it's never too early to study competition math if you are genuinely interested in math. Andy happens to be that kid. I don't think his parents really push him that much, but he really likes to study math. That's all I know. That's all I can tell about Andy's story. So, if you don't like math, it's okay. But there might be a case where you actually could have liked math. It's just somehow your supporting environment did not allow that or did not make that happen. I don't know what could be the secret sauce for making kids genuinely interested in math, but I don't think you should be forced to study math if you don't like it. Okay. My son's case clearly educated me like that. When Aaron was not interested, no matter how hard I push it, it never happened. So he became interested or willing to study math only I told him, well, this is your last chance. You're in 8th grade. If you don't do this now, you will never even have a chance to try it. I don't know how much that played into his decision, but it happened and it worked. So those are two contrasting stories I'm telling you today. I spent this much time because today is special. After much deliberation for this particular program, I don't think it's very meaningful because this is my third season of doing this. I'm trying doing this every year with live sessions, but it turned out I think this year the students who attend live sessions went down quite a bit. For the first 2 years, I usually have above 100 students for each live lecture. And I guess the reason is that since now almost literally every school went back to normal school schedule, we did not just have those kind of live just network-based online lectures anymore. People will not be able to find time to attend online class in real time, if assume they will watch the video or replay. Because of that, I don't think it's viable or is even meaningful for me to continue providing live sessions for this training program, because I do have videos, almost exactly the same content every week from the previous season. I think it will be most appropriate for me just to relink those older videos for each week, because the content would be exactly the same, almost exactly the same. Every week, the Mathcounts mini the same, and we will discuss about the same solutions. So it makes more sense to just let people watch the replay videos. So this is the last live session I will provide for this 13-week Mathcounts training program. However, the training program effectively remains same, because you will get exactly the same amount of information. I will make a YouTube video playlist, list all the 30 lectures, the videos. But it's just that any student who want to just get something out of this training, you need to be very disciplined, because I understand if there's a live lecture, students feel a little bit more obligated to attend. If you just say, hey, there's a video there, you may find a time to watch, maybe that will never happen. But seriously, as middle schoolers, maybe some of you younger, you need to understand that it's your choice. Your future will be in your own hands. You have control of your future. So if you want to watch the videos and learn, that's great. If you procrastinate or find an excuse not to do that, you know what you are doing. So that's that. So as mentioned, this will be our last lecture, live lectures. And starting next week, actually every videos will be relinked at the this program webpage tonight. Just watch them or not watch them at your own, just a pleasure. So with that, let's go to this week's materials. So this week is week number 18, algebra. Okay, let's go to our first problem. So this is our first problem. Show that any group of 7 integers, 2 of the integers have the same remainder when divided by 6. Some of you who have already learned this kind of just trick should immediately recognize what this problem is all about, right? But if you have not, you may struggle a little bit, but actually that's a good thing, because I'm a strong opponent for treating competition math as memorizing formulas, tricks, and so on. Also, the trick here is extremely standard. This will invoke the so-called pigeonhole principle. And what is a pigeonhole principle? Well, just think about a pigeonhole case. Let's just say you have 5 pigeonholes, and you have 6 pigeons. You want to put them into those holes. What will happen? Because you have more pigeons than the pigeonholes, at least there will be one hole that has to host at least 2 pigeons. If you want to put all the pigeons in those pigeonholes, no pigeon will be left outside. Then, because you have more pigeons than holes, at least one hole will at least host 2 or more pigeons. And this general principle is called pigeonhole principle. So in this problem, it's something just calls for that principle, because you have 7 integers, right? And when you divide an integer by 6, how many cases you can have in terms of the remainder you can have? You have number n. Let me use a red pen. This is too small. So let's say you have a number n divided by 6. We are talking about integers here, perhaps positive integer, but it doesn't matter whether it's positive or negative, but let's just say it's positive. You have a quotient, and then you have a remainder, right? I'm using this notation poorly because this is not a good notation, but we're just trying to make a point. If this integer happens to be a multiple of 6, then you get a integer quotient and no remainder. For example, you have 24. 24 divided by 6, you get 4, and you have no remainder. Remainder is 0. But what if you have 25? Then you get still 4 as quotient, but the remainder is 1. So you continue this process until you got 29 divided by 6. Still quotient is 4, but the remainder now is 5. Right? 29 divided by 6. 4 times 6 is 24, so the remainder is 5. If you get one more into the dividend 30, what will happen? You get the quotient as a 5. Now the quotient will go up because you just get enough, big enough for the dividend. Now what happened to the remainder? Remainder goes back to 0. So now you can clearly see this process will repeat. So the remainder will recycle among those 6 numbers from 0 to 5. And this is very easy to understand. If you keep doing this, the remainder will wrap around starting from 0, 1, 2, 3, 4, 5, then goes back to 0, then 1, 2, 3, 4, 5. This will repeat forever. So clearly, this is some very important basic fact in number theory. The remainders here can only be from 0 to 5 when the divisor is 6. So the number of remainders actually is exactly the same as the divisor because you have 0 there, and you cannot have the divisor itself as the remainder because then you will have enough to get one more in the quotient. So therefore, when you divide integers by 6, the number of possible remainders will also be exactly 6, and that starts from 0 through the number that's exactly 1 less than 6, which is 5, from 0 to 5. So you got 6 remainders there. Now, with that understanding, when you look at this problem, you have 7 integers. They are all divided by 6. So 7 integers, each integer will result in a remainder somewhere from 0 to 6. So you only have 6 choices for the remainder, but you have 7 numbers. So we just proved by applying the pigeonhole principle that within this group of 7 integers, 2 of them must have the same remainder. That's a straightforward application of the pigeonhole principle because 7 is greater than 6. Like you have 6 pigeonholes. Those are the remainders from 0 to 5. But you have 7 pigeons. You have 7 numbers. So 2 of them got to be in the same pigeonhole. That means that 2 of those numbers must have the same remainder. Okay, so this is an extremely simple application of the pigeonhole principle, but if you have never learned it, you have just learned it. All right, so very straightforward. Also, it's a little bit surprising. I'm not sure whether this was really a Mathcounts problem. It doesn't look like a Mathcounts problem because a Mathcounts problem will never ask you to provide a proof. Also, in this case, proof is actually quite simple. Okay, so that's our first problem. Second problem. I have 46 pieces of candy that I'm dividing among myself and 4 friends. Explain why at least one of us receive at least 10 pieces of candy. We just talked about pigeonhole, right? So actually, in the basic version of pigeonhole, you say that just you have n holes and you have k pigeons. When k is greater than n, you will have at least one hole that holds 2 or more pigeons. This principle can be easily extended to a stronger version as pigeonhole. It's a stronger version, but still essentially pigeonhole. Let's just say you have a k that is greater than mn. You still have n holes, but now you know your number of pigeons is not just greater than n, but more than m copies of n. Now you put those k pigeons into n holes. What happened? It can be easily seen and reasoned that at least one hole will host at least m plus 1 pigeons, right? The reason is exactly the same. You divide this k by n, you get at least m, then some remainder. So you try to minimize the number of pigeons in each hole, and you can try to distribute them equally. But once you have already put m pigeons into each hole, you have only hosted m times n pigeons, but then you have some remaining pigeons. They have to go somewhere. So you can see that at least one hole will host more than m pigeons. So essentially, this is exactly the same reasoning as the basic version of the pigeonhole principle, but it's just more general. If m equals to 1, then this will roll back to the basic version of the pigeonhole principle. So this problem is actually an application of this extended version or stronger version of the pigeonhole principle. So because now we have 46 pieces of candies, and we are trying to divide in those candies among 5 people, right? Myself and 4 friends. There are 5 people here. They try to divide those 46 candies, and 46 is 45 plus 1. 45 is a multiple of 5, which is 9 times 5. So you can see that at least one guy, either myself or one of the 4 friends, will receive 9 plus 1 candy, meaning that we'll receive at least 10 candies. So this is just a little bit more complicated than the previous problem, but essentially the same. It's still a pigeonhole problem. You put 46 pigeons into 5 holes, and 46 is 1 more than 5 times 9. Therefore, at least one hole will host 9 plus 1, or 10 pigeons at least. So that means that at least one of us will receive at least 10 pieces of candy. Okay, so those first 2 problems, easy, pigeonhole. If you never heard of it, now you have heard it. Okay, this problem is a little bit tricky. Show that in any group of people, there are 2 people in the group who have the same number of friends among this group. Yeah, it sounds like this could be a pigeonhole problem one more time. Until you think that what is pigeon and what is hole. Okay, so at least 2 people who have the same number of friends. That sounds that the number of friends sounds like that's our type of pigeons, not the pigeonholes, right? Because you have the same number of friends. So the number, the number of friends sounds like the pigeons. But then what is hole? Okay, so it's not immediately obvious how we can map the concept of the pigeons and the pigeonholes onto this problem. So why don't we just forget a pigeonhole principle for a short while and take one step back to think about if we don't know those terms, what will happen? Well, we will have 8 peoples. Each person will have some friends within this group, right? It may not happen that this guy or girl has a friend, but in mathematics, we treat that the same as having a friend. We just assign a 0. If you have 0 friend, you don't have any friend, but you still have a number associated with you, a number of friends that is 0. So with 8 people, how many friends you can have? You can have actually from 0 to 7. You may have no friend at all, that you have 0 friend, or everybody is your friend, you have 7 friends. So you have 0 to 7, that's 8 choices. This doesn't sound like the right number for the pigeonholes because we have the pigeonhole principle says that you have more pigeons than the holes, but here we have 8 choices. Sounds like this should be the pigeonholes. But if we have 8 holes, then we got 8 people. Everybody can get a different number. We just got enough. The same number of pigeons as the holes, right? It sounds wrong. It sounds right at first glance, but you have to be a little more kind of just alert about logic. Let's just say we have a choice and everybody get a choice. 8 people, 8 choice. Those 8 people, they got 0 friend, 1 friend, 2 friends, until 7 friends. Everybody has such a choice, and they are all excluding each other. Sounds good, right? Until you have to find something wrong. And what is that? What is that? If you have 8 people, they have those friends, 0 friends, 1 friend, 2 friends, 7 friends. If that's indeed the case, you have an inherent contradiction. Because there are 2 extreme cases. One guy has 0 friends, and another guy has 7 friends. Can those 2 actually coexist? Can those 2 cases happen at the same time? Someone has no friend, meaning that he doesn't like or nobody likes him or he doesn't like anyone. But another guy has everybody as his friends. Apparently those 2 cases cannot happen at the same time. Therefore, you can either have 0 or 7. You may not have neither of them. You may not have either one of them. But you just cannot have both at the same time, right? It cannot be that one guy has no friend and the other guy has everybody as his friend. Those 2 cases are inherently contradicting each other. Therefore, your actual number of holes is at least 1 less than 8. At most, 7, not 8. Therefore, we don't know whether it's 0 or 7, but we don't really care. All we care is that you can only have 7 possible cases in terms of the number of friends those people can possibly have. Either having zero or either having 7 or none, neither. But you just cannot have both. Therefore, your maximum number of pigeonholes is 7. But you do have 8 people. Therefore, there are 2 people in this group who have the same number of friends among the people in this group. Maybe those 2 people, they neither have any friends, both have 0 friends, or both have 4 or 5, or both have 7, but 0 and 7 cannot happen at the same time. So we just once again use the pigeonhole principle to prove this problem. The trick here is that initially you may find 8 holes, then upon further investigation, you rule out that case. You can only have 7 holes, not 8 holes. Okay, at most 7 holes. Okay, so we had a quite interesting run on pigeonhole principles. Those 3 problems, I think they're very good to help you understand this very important principle. Okay, I think in AMC, Mathcounts, this will be tested. Okay, I think we might have studied a problem like this before, but it doesn't hurt. It's been a while. Let's just review one more time. You have a plus 1 over a, the reciprocal of a equals to 6. And then what is a to the 4th power plus 1 over a to the 4th power? How do we do this? Well, if you recognize that there's some special link from this one to this one, then we already know this. We already know this is how many? 6. How do we go from here, from left to right? There must be something, right? Well, what is the unique thing about this? Unique thing is about in both cases, the 2 numbers being added, they're reciprocal of each other. That's a very important and interesting fact. But how do we make a connection between those 2? Well, because the only thing that we can manipulate is this algebraic expression, we have to do something about it. So you think about doing something upon this guy, a plus 1 over a. Somehow you want to lead to this guy. Shall we? The most obvious case would be, can we do this 4th power? Yes, you can, but this will make things much more difficult because by the binomial theorem, this will expand into a lot of terms. Okay, so that's kind of discouraging. Is there a better way to get there? Well, maybe just using this analogy. When you fly from San Francisco to New York, this is San Francisco and this is New York City, you prefer a direct flight, right? If you have a direct flight, yeah, that's very convenient, but that could be quite expensive sometimes. And if you don't care about some delay, you may want to make a connection in Chicago. This is Chicago. You fly from San Francisco to Chicago, then transfer to New York City. That means that you don't have to go to New York directly. You may take an intermediate stop and go from there. And that's exactly what we'll do here. From a plus 1 over a to get to this term, it's quite difficult, also not completely impossible. But what if we take an intermediate step? What if we don't do 1st power, we only do 2nd power? Can we go from here to here? Well, by the same logic, you want to take a square of this. That will at least give you those two terms. Now you see, because we are much more comfortable with binomial squares than higher power of binomials. Binomial square is really well studied and well understood. This is equals to a square plus 2ab plus b squared. Whoa! Now we see what happened. We have this term 2ab, but the a and the b here are a and 1 over a. They're reciprocal to each other, so when we multiply them together, they happen to cancel out each other, give us just the nice number 1. So this is actually a squared plus 2 times a times 1 over a, which is 1, then plus 1 over a. So this is just a constant number 2. That means that we can get this one by subtracting 2 from this guy's square, right? We just need to subtract a constant. Constant not a big deal, especially a small number like 2. So easily a square plus 1 over a square equals 2. We take a square on this guy, that's 6 squared. Let's subtract 2. That's it. So we know a square plus 1 over a square is 36. Subtracting 2, that's 34. Now you see there are two ways to go from here to the fourth power. We need to go from this Chicago stop to New York City, which is right here. Well, by the same logic, you can square this again. You will see that will essentially go through the same process, because this time it will be 34 squared subtracting, because now we have a squared times 1 over a squared. That's once again get cancel out, became a number 2. So this is actually 34 squared minus 2 to give us this. Or similar but conceptual different, because we just did what we did. If you just treat this a squared as 1 or use some algebra, this became exactly the same problem where we start with, except the numbers are slightly different. So if you choose a squared equal to b, then what we had here is b plus 1 over b equals to 34. Now, because a squared equals to b, so a to the fourth power is simply b squared. So if we know this, we want to get this, we just do exactly the same thing we just did. This is just different look at the same trick. Okay, so whether you square the square or square a different variable b, doesn't really matter. You essentially go through the same thing. So now the answer to the original problem is just 34 squared minus 2. And what is 34 squared? Well, I have to go back to my human calculator. So because in Mathcounts, in this, I believe this cannot be a target problem. So this is probably much easier to do with hands. So this is 1156 subtracting 2, that's 1154. Okay, very good. All right, next problem. Okay. We have 3 variables x, y, z. We know their product is 45, and the very bizarre condition, that is the sum of their reciprocals, 1 over x plus 1 over y plus 1 over z equals to 1/5. Then what is the arithmetic mean of the 3 products x, y, y, z, and x, z? So what we have here is we know 2 equations, x plus y plus z equals to 45. Oh no, x times y, I'm sorry, x times y times z, not plus. So x times y times z equals to 45. And we know the sum of their reciprocals is just, oh, that's 1/5. So we know two equations about rows. Usually, you know that this does not help that much because we are still short of one more equation about row 3 variables, right? You know, with just two equations for 3 variables, you cannot solve the equation because there are infinitely many solutions. They're kind of undetermined. So, but what do okay, good job, Mathcounts. Microsoft actually. So we just need to figure out what is xy plus yz plus xz divided by 3. That's what we need. So essentially, you need to figure out a way from those two given conditions to find a way to generate this expression. From here, it doesn't look that obvious, but we know we don't like expressions like this guy, which is a lot of reciprocals. So why don't we just do a little bit cleanup of this expression to see what happens? So this is nothing but xyz as the common denominator. Then in the top, the numerator positions, we 1 over x, that's really yz. Then plus y over 1, that's xz. Oh, wait a second. This is exactly what we are interested in. So this is actually almost there, right? We want to the 3 variables products, add them up, but we have that here, and this is 1 over 5. But we also know this. Okay, so now the result is very obvious. Because we know this, we will be able to go from here to the fact that yz plus xz plus xy equals to 1/5 times xyz. But we know xyz, the product is 45, so this is 1/5 times 45. This equals to 9. If we know 9, of course, it divided by 3, that would be 9 divided by 3 equals to 3. So this problem, you think that this is kind of intimidating. It's actually extremely simple. Your guess will work perfectly if you first start with this fraction, which you don't like, and if from there you will see what you get is very close to what you need to solve. So therefore, this problem is actually quite easy. Okay. All right. We have yet another algebra problem here. The difference between the squares of two positive integers is 2009. So from that point on, you immediately write the equation, right? Because this is as close to as the description of equation as it can get. The difference between the squares of two positive integers, so it's just x squared minus y squared. The difference between the square of two positive integers, and of course here we assume both x and y are positive, is 2009. So this is immediately characterize every piece of information except whether they're positive in the first sentence. What is the maximum possible difference between these two integers? So we need to the maximum possible difference. So here we apparently assume x is greater than y because they are both positive. If y is greater than x, this would be negative. So that cannot happen. So when we do this, we already assume x is greater than y. So the problem asks you to get the maximum possible difference, right? Now we have to subtract y from x, because if we subtract x from y, we'll get a negative number. So that's not something we want to max as possible. So we really want to, what is the possible value of this x minus y, and at the max. Okay, so how do we connect those two things together? We know we are constrained by the first equation, but that didn't help us solve the equation. But remember, x and y are integers. And this sounds too nice not to do something about it. X squared minus y squared, that's difference of squares. We immediately know this will be x plus y times x minus y. That's how you factorize the difference of squares. Hey, wait a second. This is the guy we are interested in, right? So 2009 is the result of the product of x plus y times x minus y. And now we want to know the maximum possible value of x plus y. Because the product of two numbers is 2009. So that means that if we want this to be at its max, meaning as big as possible, then x plus y must be at its minimal, as small as possible. But how do we know where is the minimum? Of course, we can prove the minimum of x plus y is something. Then we will also know immediately the maximum of x minus y will be something determined by that first number, because the two multiplied together equals to 2009. Okay, that's a big constraint. So what is the minimum of x plus y? We don't even know what x and y's are. But wait a second, because they are integers, so both x plus y and x minus y must be integers, so they need to be the factor of 2009. Okay, 2009 doesn't sound a very kind of easy number to factorize, right? It's not like something like a 108, 240, and so on. 2009, we don't even know whether it's a prime number. So at this time, you have to little bit factorization of 2009 to see what it is. Because if it's a prime number, then we are out of choice. Okay? Because x plus y and x minus y have very limited choice. Because if 2009 is a prime number, so it must be that x minus y is the smaller of the two, is 1, and x plus y is 2009. But we are not there yet. We first need to see whether 2009 can be further, just can be factorized. 2 plus 9 is not a multiple of 3, so we know 3 is not a factor. Of course, 2 is not a factor, because this is an odd number. How about 5? 5 is not. 4, 6, all those are not. How about 7? 7. 2009 divided by 7, what will we get? 7, that's 3, no, 21, too big. 2, 14, we got 6, 0, that would be 50, 56, 7 times 8, 56, we get 4, 4 and 9, 49. 49 is a multiple of 7, so we know that is 287 if we divide it by divide this number by 7. So we at least take a first step, factorize is 7 times 289. Now the question is 289 factorizable? Well, here comes the fundamentals, okay? This is the basic fundamental. 289 is the square of 17. You don't believe it? Grab your calculator. Prove me wrong, and you cannot. So, we get it. So the factorization of 2009 is just this. Now everything is prime, 7 and 17. So how many total factors does this number have? Because we know there's a formula, this is 1, so it's 1 plus 1 times 2 plus 1. So this number has a total of 6 factors. And that means that 2009 can be represented in 3 pairs because you have 6 factors, and this is not a perfect square. So 6 factors means that you have 3 pairs of factors that each pair consists of 2 numbers that can be multiplied into 2009. So apparently the first pair is just 2009 times 1. And the second pair, we take 7, so that's 7 times 289. The third pair, we take 17 first, so that's 17 times 7 times 17. 7 and 49, that's 119. There's no other possible factors. If you know the formula of the number of factors, you just, once you do prime factorization, you just add the exponent by 1 and multiply them together, so that's 6. So we are very confident that those are the only 3 possible ways to factorize 2009. But you see that for each such product, it needs to be matched x plus y and x minus y. And assuming both are positive and x is greater than 1, we know 2x plus y is bigger. So in the first case, we would have x plus y equals 2009, and x minus 1 is just 1. And this will give us x is just 1 plus 2009, that's 2010 divided by 2, equals to 1005. Remember, this is x plus y. We want this as small as possible because we want x minus 1 as big as possible. For example, in this case, if it's x is 2005, then y is just one less, so y equal to 2004. No, this doesn't sound good. This is too big. So how about the second choice? If it's 289 and x minus 1 is 7. So in this case, x would be 289, that's 296. 296 is 148. And y now is 141. It's 7 less than x. Okay, in this case, what would be x minus y? It's 7. So clearly, now you see, you don't have to go through that process. After you do the factorization, you just take the smaller one as x minus y. And you want to be this one as big as possible. So in this case, the third one is what we want. Because in this case, 17 will be our x minus y. Okay? So you immediately see you don't have any other possibilities. So 17 times 119 is your decomposition of 2009 into 2 numbers. And in this case, 17 equals to x minus y. And 119 is x plus y. Okay? All right. So let's solve this problem, didn't we? What is the maximum possible? So here we got the maximum smaller one, which is 17. Okay, we have one more. How many problems do? Oh, we have 2 more problems. Okay, not a problem. So 3 consecutive positive odd integers. You have in Mathcounts, you have to read the problem very carefully. Don't just overlook anything. So 3 consecutive odd integers, not just consecutive integers, but positive odd integers. A, B, C satisfy b squared minus a squared. So we have 2 equations, and we know they are consecutive. So it's actually, we just need to make a decision. So we know there's a relationship here, right? They are consecutive. So A, B, C, they form a arithmetic sequence. And we know here A, B, C just B minus 2, B, and B plus 2. That's what consecutive odd integers is. But we know they are consecutive spaced by 2, but there's no indication B is odd. So a better way to represent this is write B as 2k plus 1, and the next one will be 2k plus 3, and the previous one will be 2k minus 1. And you can see why, because we need to guarantee they are all odd numbers, and they're separated by 2. So this is a better way to represent the original one. But what is the algebra here? So b squared minus a squared, okay, and that means that the square minus this square, so 2k plus 1 square minus 2k minus 1 square. Well, this is the difference of squares. We know how to do that. So this is 314. Okay, okie dokie. So what can we do? Well, we don't want to expand this immediately. We will use difference of square. So that will be 2k plus 1 plus 2k minus 1 times 2k plus 1 subtracting 2k minus 1, right? It's just a kind of just factorizing this. So this is 4k plus 2 times 2k plus 1 minus 2k minus 1, that's 2, okay? Equal to 344. So you can see that we can solve the k immediately by first dividing this by 2, that's 172, then subtracting 2 divided by 4. Agree? So this is first divided by 2, give us 4k plus 2, then subtracting 2. Then we get this 170. Hold on a second. Is that correct? Oh, wait. We don't actually need to solve this k, don't we? We just need to solve c squared minus b squared. And what is that? C squared minus b squared. That's 2k plus 3 squared minus 2k plus 1 squared. And by the difference of square, we know this is a 4k plus 4. 4k plus 4 times 2. We just need to evaluate this. But since we already got this, you can easily see how this will work out. Because this is related to this by as adding 4 to that, you will get what we want. Okay, so this is actually 348. Okay, so today's algebra, I think in general, they are very simple. All right, we have one more problem to go. And this problem is, oh, it doesn't sound very interesting. Grade and minus age plus the square of grade angle plus age is. Anytime you see a number related to age that big, you feel this is not real, right? But we talk about a square, so that must be a very big square. So why don't we write this as equation a plus p squared, m plus p squared equals to 7,308, where m represents the age of Minnie and the p represents the age of Paul. So that's the first condition. Great uncle Paul's age plus square of ages. We got a square sum. Okay, so p squared plus m squared equals to 6974. What is the sum of m and p? So we just need to calculate p plus m. So this is very important, okay? Very, very important. Don't get lost. The problem never asks you what is the age of Paul, or what is the age of meaning. You may swap them, but you don't have to, because eventually you just need to know the sum. Sometimes this is actually easier, if not way easier, than calculating par and m individually. You don't need that. If you can figure out what the those values are, you can get a p plus m, but that might be overkill. You may be able to find the p plus m without knowing exactly what p is or m is, but only they're constrained by this relationship, p plus m. Okay? Okay, how do we do that? Well, when you have something like this, m here, m squared like here. Oh, sorry, the second equation is p squared plus m squared. Yeah, that's what. This square cannot be there. Yeah, that's perfect. When you see something like this, you feel that you want to do algebraic manipulation, but how do we manipulate those two equations? This calls for your basic skill in polynomial factorization. Because if you are really good at that, you will see that if you add those two together, you don't get much information. P squared plus m squared, that's just without another degree 2 polynomial p times m, you really cannot do much about that. You cannot factorize anything. But what if you subtract the second one, which is smaller from the first one? Then you see that because they kind of just alternate symmetry there. You have m here, but you have m squared there. But you have p here, but you have m squared in the first one. So if you subtract them, you get some p squared minus m squared plus m minus p, right? Now you see how you can do this. You can do factorization. This p squared minus m squared, that's p plus m, p minus m, minus p minus m. Why we want to use p minus? Because that's closer, actually matching this. But we have to change the sign. Now you see that you can factorize this. P minus m times p plus m minus 1 equals to originally 7,308 divided by this 6,974. This is nothing but 308 plus 26. So from this point on, you know what this is all about. It's just once again, you need to do factorization. And what is this number? This is 334. Is that right? Yeah. Okay. So this is 334 equals to those two. But 334, how can we do the factorization? You get a 2 times 167, right? 167 is 167 prime. Is 167 prime. We have to check, right? We only need to check up to 14 square, 13 square. So 2, no, 3. 1 plus 6 plus 7, that's not a multiple of 3, so 3 is not. No 5, no 6, obviously. How about 7? 7 will give 160, that's 14. 2, 7, 27 cannot be divided by 7. No. Another way to think about it is 168. It's a multiple of 7, clearly. That's times 14. No. That's 168 divided by 7, that's 24 times 7. But this is 167, one that, so it cannot be multiple of 7. 8, no. 9, no. 10, of course, no. 11, no. 12, 13, 13. 13 squared is 169. That's already bigger, so 13 is not. Now we know for sure this is a prime number. Okay, remember this is very important. In this case, it happens to be a prime, but in a typical problem, you need to carefully verify it's indeed not a prime. So it's 167 times 2. That means that which number looks bigger? Clearly, this looks bigger. This is plus m. This is minus m. Difference 2m. Also, you do need to subtract 1, but 1 is just 1. So clearly, this is a bigger number. This is equal to 167, and this equals to 2. So that gives us the solution, right? P plus m minus 1 is 167. P minus m is 2. So P equals to 167 plus 1, which is 168 plus 2 divided by 2. All right, this is 170 divided by 2, that's 85. What do we need to know? We know the sum of P and M, but from here we can easily figure out M just 2 less than P, M just 83. Okay, so that means that P plus M just 2 times 84, the median between them, that's 168. Not too bad for them to have such long longevity. Okay, so that's today's Mathcount training, and as I mentioned, starting next week, we will just post videos. Okay, if you are in 5th grade, 4th grade, you are not eligible for Mathcounts this year, stay tuned. Keep practicing 10 Mathcounts next year. Okay, that's all for today. Thank you, and see you somewhere else.